So today we're going to start by using the same technique that we had used last time in order to solve more complex differential equations. So we'll have the following example. And in this example, we're just going to be solving a bunch of these. So find the solution of the following equations. And the first one here is going to be y prime, which is equal to x over y. Okay, so here we only have one differential equation, which means that we are only going to be able to find the general solution. We're not going to be able to find the particular solution, because to find the particular solution, we would need an initial condition. Right, so we're going to start with this equation and just try to find the general solution. So I'm just going to write this down. We only should find a general solution because there's no initial condition. Now, the first step is always going to be to write y prime as dy over dx, right? Because based on what we did last time, what we're trying to do is separate the variables. We're trying to get everything that's in terms of y on one side, everything that's in terms of x on the other side, so that then I can integrate each side independently, right? So a part of that is to write the derivative as dy over dx so that I can split the dy and the dx. So I have y prime over here is equal to x over y, which means that dy over dx is equal to x over y. And we said what we're trying to do is put everything in terms of y, so the dy and the y on the same side, and everything that's written in terms of x on the other side. So what we're going to do here is just multiply both sides by dx, divide and multiply both sides by y, which means that we would get y times dy is equal to x times dx, right? So I multiplied dx on both sides, simplified on the left, and is still on the right-hand side, and I multiplied both sides by y, which simplified it on the right-hand side and made it appear on the left-hand side. So now I can integrate both the left-hand side and the right-hand side. And in the left-hand side, I'm going to have y squared over 2. On the right-hand side, I'm going to have x squared over 2. But on each one of the two sides over here, I'm going to have a constant of integration, right? So this is going to be plus constant 1, and this is going to be plus constant number 2. Okay, so the constant on the left-hand side and the constant in the right-hand side. And these constants are just constants of integration, which means that they can take any value that we want. Now, I'm trying to solve for the function y in terms of x, which means I'm going to try to multiply everything out on the other side. So that means I'll have y squared over 2 is equal to x squared over 2, and then plus c2 minus c1. Right? And then because C2 can take any value that we want, it's an arbitrary constant, and C1 can take any value that we want, it's also an arbitrary constant. That means that C2 minus C1 is going to be an arbitrary constant itself. It's going to be any possible value that we want. Right? So what we end up with is that y squared over 2 is equal to x squared over 2 plus c. Okay. Now, if you look from this step to this step, you're going to realize that this is the same as if we had just integrated the left-hand side without adding a constant of integration, and we had just added the constant of integration on the right-hand side. So that's essentially what we're going to be doing when we solve differential equations, because you're always going to end up combining the two constants from the left-hand side and from the right-hand side. Instead of having this repetitive step that we have every single time, what we're going to do is always integrate the left-hand side without an integration constant and put the integration constant on the right-hand side. That way we are skipping these middle steps over here that are not useful anymore. All right, so we'll have y squared over 2 is equal to x squared over 2 plus c. And because I'm trying to solve for y, I'm going to try to solve for it now. So I'll have y squared is now equal to x squared plus 2c, which means that y is equal to either plus or minus square root of x squared plus 2c. Any question? Can I see a show of hands for those of you who understand everything that we did here? All right, good. So we have that y is equal to plus or minus square root of x squared plus 2c. You're going to see when you're trying to find a solution, we're always going to try to write it in the simplest possible form. Now, because the number c is arbitrary, it's just any constant that we want, the number 2c is also going to be any number that we want. And so that means that 2c over here, we can relabel it as just some other number d. Going to do that pretty frequently. And so that means that my solution to this is going to be y, which is equal to plus or minus square root of x squared plus d. And the important part here is that whether it is plus or minus, so whether it is plus or minus, depends on the initial condition, right? So we say, if my initial condition tells me that the y coordinate is going to be positive, then that means that my actual solution is the positive root, whereas if my initial condition gives me a negative value, then that means that y is going to be given by the negative root of x squared plus d. And the value of d, of course, is also determined by the initial condition. Right? Parsley, you still have your hand up? Right. So I'm going to write the second equation on the board, which is b is equal, so y prime is equal to x times y divided by x squared plus 1. And then y of 0 is equal to 5. Okay, so write this down and then maybe start this in a little second. Yes, Megan, there's a question?
Yeah, I don't know if this is like normal or not, but we've already done these examples.
We've already done these examples. Oh,
yeah.
Okay. What's the last example that we covered?
It's a metal company has their production increasing at a rate proportional to the product of the number of units n, like that one.
Okay, did we finish that one?
It looks like yes, we did.
Oh, okay. Then we have done way more than I thought we had covered. I was convinced that we hadn't done that much. Oh, let me go through this. Okay. Oh, okay, we've only lost 10 minutes. Thank you, Megan.
You're welcome.
All right, it looks like it wasn't just a long weekend. Guys, it was a long weekend for me too. All right, so then we'll start with the next example that I had in line, which was an example about bacteria population growth. And then we're going to do a more difficult one, and then I think you'll be all set. I was convinced that we had less than that, but it's good. So, example. We have that a bacteria population, and you might have something that's similar to this regardless, but it's a classic example, so it's going to be important to know how to model these. So a bacteria population grows at a rate proportional to its size. Initially, 250 bacteria are present, and after 3 hours, there are 1,000 bacteria. 1,000 bacteria. Okay. So the question over here is how many bacteria? Okay, so the first question is to find the function P. And to find the function P, we're going to have to set up the differential equation that models this problem, and then we're going to have to write down the initial conditions that we have in order to find the different parameters of this type of expression. All right, so we'll have first that dp over dt, so p prime, or dp over dt, is equal to, so this bacterial population grows at a rate that is proportional to its size. That means the rate of growth, p prime, is proportional to the size of the population. Then we have that initially 250 bacteria are present, so p of 0 is equal to 250, and p of 3 is equal to 1,000. Right? Which means that dp over dt is the first thing that we're going to solve, this differential equation, and then we're going to use the other initial conditions in order to find the values of the constants that we don't have yet. So we have, this is k times p, which means that if I divide both sides by p, I'm going to have 1 over p dp, and on the right-hand side, I'm going to have k times dt. By integrating both sides, we have that ln of p is equal to k times t plus c. And then I have to solve for p. So if you have tried any problems so far, then you might have realized that it is really important to be able to solve equations that involve logarithms and exponentials. And so what we're going to do here is put everything on the exponent of e. So we have e to the ln of p is going to be equal to e to the kt plus c, which on the left-hand side will give me p, and on the right-hand side, it will give me e to the kt times e to the c, right? Because e to the something plus something, I can split that power and write it down as a product. So then I'll have e to the power of c, which means that p is equal to some constant a times e to the power of kt, where all I have done is write e to the power of c as my constant a. Right, and that's because the value of c is arbitrary. If you understand what I've done so far, please raise your hand. Okay, that's good. That's good. I thought we were a lot more behind. I think I caught up with the wrong part. Okay, so that's good. So that means that now we're going to use the two initial conditions that we have over here in order to find the values of a and k, which makes sense because we have two constants to look for and we have two equations that are going to help us find those constants, right? So that should always be the case. If you have one constant to find, you need at least one initial condition, whereas if you have two constants to find, then you need at least two initial conditions. So the first is that p of 0 is equal to 250, which means that I'm going to make this equal, I'm going to make this equation be true, and that means I'm going to have p of 0 is equal to a times e to the power of 0, which is equal to a, right? And that's going to be equal to 250, because that's the value that's given. So what this tells me is the constant a is equal to 250, which means that I now know that my population is given by 250 times e to the power of kt. So that means population is given by 250 times e to the power of k times t. Now here, something that might be useful for you to remember is the fact that if you're given always, so if you have a population growth model that is exponential, so just this, if you have p prime times, which is equal to k times p, and you're given the value when t is equal to 0, then you're going to automatically be able to say that the constant that's multiplying this, the value, the constant that multiplies the exponential over here, would be the value at 0, right? And that's because at that value when t is equal to 0, this term over here is going to become 0, and e to the 0 is going to become 1. Okay, so that's just a good check to have. The next thing that we know is that p of 3 is equal to 1000, which means that p of 3 is equal to 250 times e to the power of k times t, which is 3 times k. And this is going to be equal to 1000. Now, at this point, we're going to have that e to the power of 3k is going to be equal to 1000 divided by 250. We're trying to solve for k, remember, 250, which is equal to 4. And this means that 3 times k is equal to ln of 4, right? Where all I have done is taken the natural logarithm on the left-hand side and right-hand side of this expression. So if this is not automatic to you yet, then you need a little bit more practice, but anytime you have e to the power of 3k, the way to recover that exponent is just to take the natural logarithm on both sides. Because if you remember well, the natural logarithm tells me the exponent that I need from e in order to get a given result. And so if I take ln of e to the 3k, the exponent that I need from e is just 3k. That means 3k is equal to ln of 4, which means that k is equal to ln of 4 over 3. And this is going to now help me replace things in my expression for p over here. So that means that p is equal to 250 times e to the power of ln of 4 over 3 times t. I can rewrite this as 250 times e to the ln of 4 times t over 3. And that's always the reflex that I have, because what I want to do is to be able to simplify the exponential and the logarithm for the piece at least that contains a logarithm, right? So over here we have e to the ln of 4. I know that that's what I want to simplify, so I'm going to separate the ln of 4 from everything else in the exponent. Now, e to the power of a times b is the same as e to the power of a, the whole thing to the power of b. And so that means that p is equal to 250 times e to the ln 4, which is just 4, to the power of t over 3, right? So I write my final answer over here. This is that the population as a function of time t is going to be 250 times 4 to the t over 3. Can I see a show of hands, please, for those of you who understand this? Okay, I only saw about 12 hands, so please keep your hand up if you understand. If you haven't raised your hand, raise it so that I can make sure that everyone here has a pretty good idea of what you need to do. Okay, I have still 7 people that have not claimed to understand this. Is there a part in, like a piece in particular that seems a little bit more difficult than the rest? The last part, so finding the simplified expression, is that what you're referring to, Erin? So what I have now is I found the values for A over here, and the value for k, right? And all that we did now is in the expression that I know gives me p, which is p is equal to a times e to the kt, I replaced both of those things. So I have 250 over here and ln of 4 over 3. Now, because I have e to the power of ln of something, and I know from previous classes that e to the power of ln of something is just going to be equal to the something that's inside the logarithm, I know that there will be something that I'll be able to replace at this point. Right, so the e to the ln of 4, at some point I should be able to simplify it. Now, the thing is that I only have to have e to the power of ln of that something if I am to simplify it. So what I'm trying to do now is to split the ln of 4 from the 1 over 3. So what I did is I just said, okay, well, ln of 4 over 3 times t is the same as ln of 4 times t over 3. Right? So whether I'm dividing both of the terms, just the first one or just the second one, doesn't matter because division has the same priority of operation as multiplication. Right? And so I wrote it as ln of 4 times t over 3. But I can then also use the fact that e to the power of a times b is equal to e to the power of a, the whole thing to the power of b, right? And what that allows me to do is now separate e to the power of ln of 4 from everything else, right? So I have just e to the ln of 4, the whole thing to the power of t over 3. Now, e to the ln of 4, I know that I can simplify. That thing is going to become just 4. And now the only thing that's left is a t over 3 that is also at the exponent. So by simplifying that, I still have the 250 in front. Now e to the ln 4 has simplified to be just 4, and the exponent is now t over 3. Is that better, Erin? Okay, good, thanks. All right, so what I'm going to do now is to find the value at a given time. So what I'm going to ask in the next part is, what's the population size after 3 hours? Okay, so this is just a simple plug-in problem, right? So we already know the expression for the population size at any given time, and so all that we have to do for this type of problem is to plug into that expression that we know. So we have that p, the population after 5 hours, not after 3 hours, that was given, 5 hours. The population after 5 hours is going to be p of 5, so p at time 5. And that's going to be, by plugging into this expression, is going to be 250 times 4 to the 5 over 3. And if you plug into your calculator, you'll find that this will be 2,519.8 something, which is approximately 2,520. Now, in your web work, you're going to have some things to do like this. Once you find a result, you'll have to use between 1 and 3 decimals. So if you want to make sure that your answer is correct, make sure to include maybe 3 decimals, and then you should be okay, because by this point, you know that one of the big challenges of web work is to actually write the answer in the way that web work expects you to write it. Do I have any questions? I don't see any hands up. Okay. I have Parsa, Megan, and Matthew with your hands up. That might be okay, it was a fluke. And the question C over here is going to be, I'll erase while you try to work on it, or at least while you write it down. how long will it take? Will it take for the population to reach 5,000? So how long will it take for the population to reach 5,000? You can write it down, or you can and you can start working on it if you have the time. All right, so what we're trying to figure out is not P of 5,000, right? So that's the first thing that I want to say. It's not P of 5,000 because you're not trying to look for what the population will be 5,000 hours after the beginning of the experiment, but rather at which point in the experiment the population is going to be going to be equal to 5,000. So that means we're trying to solve the equation P is equal to 5,000. Now this again is going to involve some manipulation of exponents. So if you have any doubts about exponents, make sure that you interrupt me or raise your hand or write through the chat. I'm trying to keep track of everything at the same time. So for this equation, that means we're going to have to know what the expression for P is given by. That means if the population is equal to 5,000, then 250 times 4 to the power of T over 3 is equal to 5,000. And that means that I'm going to be solving the equation 4 to the power of T over 3 is equal to 5,000 over 250, which is the same as 500 over 25, and that is the same as 50 over 25 times 10, which is 20. And so that means 4 to the power of T over 3 is going to be equal to 20. This is what we're trying to solve. So we're trying to find the value of T such that 4 to the power of T over 3 is going to be equal to 20. Now, if this were a multiplication, it would be fairly easy. We know that to get rid of a multiplication, we just have to divide. But to get rid of an exponent, it's a little bit more subtle, right? It's not as easy to find the exponent of 4 that will give me 20, unless, of course, this were an integer exponent. If this were 16, then it would be really easy for me to find the exponent over here, but this is not 16, it's 20, and so I have to do a little bit of extra work. So if I want to recover the exponent from an expression, then I know that I need to apply the logarithm on both sides. I'll have ln of 4 to the power of T over 3. And on the right-hand side, I'll have ln of 20. Now, why is it interesting for me to apply the natural logarithm on both sides? Well, because I'm trying to recover the exponent over here. And I know that if I apply the logarithm on a given number, I'll be able to take that exponent, the exponent of that number, and put it in front of the logarithm. So I'll be able to turn the exponentiation by T over 3 into a multiplication by T over 3. And I know how to simplify a multiplication. Right? So the whole idea over here is I can say, okay, ln of 4 to the power of T over 3, I can take that power down, and then I'll just have a product of two things, and I know how to deal with that. That means over here, I'm going to have that T over 3 times ln of 4 is equal to ln of 20. Now, if I want to recover the value of t, I'm going to have to multiply by 3, divide by ln of 4. So that means that I'm going to have a t is going to be equal to, I multiply by 3 to get rid of the denominator of 3 over here, times ln of 20. And then I'll have to divide that by ln of 4 over here. Remembering that ln of 4 and ln of 20 are each of them a number, an exact number, but I'm just trying to find the values of each one. Now, as I've said before in the class, if you want to find the value of t, the best idea is to plug everything in your calculator at the same time, because otherwise you might end up compounding some mistakes, right? So the idea here is to write all of this in your calculator at the same time, which would be 3 times ln of 20 divided by ln of 4. And if you evaluate that, you're going to get approximately 6.48. And so t is equal to 6.48, which if I interpret in the context of my equation over here, I'm going to have that when t is equal to 6.48, the population will reach 5,000. So that means that after approximately 6.5 hours, the population will be 5,000. Now, how specific you need to be over here, how many decimals you have to include, unless I specify the amount of decimals, you can go with your gut. Here, I wouldn't want a bunch of decimals. I don't want 10 decimal numbers after the comma. What I would like is maybe 6.48, 6.5. It's good enough, right? Just to give us an idea of what we're expecting. Do I have any questions? Can you please raise your hand if you understood everything? And keep the hand up. Okay, I still have John Mackenzie and Mark that don't have their hands up. Is there any particular questions? All right. So in that case, I'm going to go to the next problem, which is going to be the most difficult version that we can have of modeling. And then if you have the time, I'll just give you some time to keep practicing problems. I know I said there was a quiz today, but I think because there is going to be a web work due on Saturday, you can start working on that. And what we're going to do is that from now on, every Friday at the end of class, you'll have a quiz, okay? So a quiz will mean that you'll have some time in class to work on a given problem, and then you'll have like 23 hours after that to submit it on layout, okay? So I'll make sure that that you have enough time to submit that on layout afterward, but it's going to be just some time to solve the problem in class. Hopefully that would be enough time to solve the problem, and then you'll have essentially 23 hours to figure out how to upload the document onto layout. Does that work for everyone? Do I have any questions about that? Questions? Okay, so web work for Saturday, that's already uploaded, and quiz on Friday as well, but by then you should have finished the web work more or less. There are just 15 problems, and they're more or less of the same level of the problem set. So for the next one, you're going to have an example which covers restricted growth. So we have that a biologist has determined that the maximum number of fruit flies that can be sustained in a carefully controlled environment is m equals to 400. So the maximum number of fruit flies that can be held in a given environment is equal to 400. Then we have that the population of fruit flies, so the rate at which the population of the colony grows is proportional to the current fruit fly population and the difference between the maximum population and the current population. The question is the following. If the current population, if the initial population is 10, and after 10 minutes, no, 10 days, not 10 minutes, and after 10 days, the population is 45, what will the population be after 20 days? Okay, so you have 5 minutes to start setting up the problem and start solving the equation. If you have any questions, you can either write them through the chat or just unmute yourself and ask them. Okay, so can I see a show of hands, please, for those of you who have started setting up the differential equation? Okay, it looks like it was a long one to write down. Maybe another 3 minutes. And if you already wrote the differential equation, then you can start solving it now. All right, show of hands if you have finished writing and started the problem. So started setting up the differential equation and tried to solve it. All right, so I'll start setting up the differential equation, and I see that there's not a lot of hands up. That's hopefully because the problem was long to write and not because you are stuck since the first step. So, but if you are, as usual, just raise your hand and I'll try to answer the questions as clearly as I possibly can. So we have that a biologist determined that the maximum number of fruit flies is equal to 400, and the rate at which the population of the colony, so rate at which the population of the colony something grows. So that means we're going to be looking at the derivative over here, right? So the rate is going to be dp over dt, where I have denoted the population at any given time by the letter p. So this is going to be proportional to the current fruit fly population. So current fruit fly population, that means the current value of p, and to the difference between the maximum population and the current population, between the maximum population and the current population. So that means that this is going to be proportional, so times some constant, to the current fruit fly population, which is just the population at time tp, and the difference between the maximum population and the current population. So that means the population, the maximum population, and the current population, which is m minus p. Now, if you wrote this as p times p minus m and not m minus p, it doesn't matter, okay? It's possible that you wrote it in that way, and the order there is not going to matter because all that's going to change is whether the value of k that you find here is going to be positive or negative. But the result is going to be equivalent, and so both of the writings here are perfectly fine. So I'm going to keep this writing over here, but keep in mind that both of them are possible, and I'm going to replace the value of m because that's already given in the problem. M is equal to 400. So that means that I can rewrite this equation as dp over dt being equal to k times p times 400 minus p. And then I have two conditions. I have the fact that the initial population is 10. That means population at time 0 is equal to 10. And I have that after 10 days, the population is 45. So that means P of 10 is equal to 45. Right? So there's two things. If the initial population is 10 and after 10 days, the population is 45. So those are two of the two conditions that I have over here. And the question is to find what P of 20 is going to be. Right? So what is the population after 20 days? Now, in this problem, there's going to be a lot of keeping track of where our terms are, and we're going to use several techniques to solve equations. So just make sure that you're keeping track of everything that we're doing and that you stop me if at any point you get confused. So first thing, as usual, is to find the general solution of the differential equation, which in this case means to find the general solution of dp over dt being equal to k times p times 400 minus p. Now, what I have here is two variables, which are t and p. And I'm going to write everything in terms of one variable on one side and everything in terms of the other variable on the other side. So that means I'm going to try to divide both sides by p and divide both sides by 400 minus p. And I'm going to multiply both sides by dt. So that will give me on the left-hand side 1 over p times 400 minus p. And on the right, times dp. And on the right-hand side, I'm going to have k times dt. Do I have any questions about this? This looks so far so good. All right, now on the left-hand side over here, and this is where it becomes really important that you know all of your techniques of integration, we need to figure out a way to integrate each of these two. So the right-hand side is going to be really easy to evaluate. That's really not the challenge that we have here. But the left-hand side is going to cause me a little bit more trouble. I have to integrate 1 over p times 400 minus p, and I don't have anything to try to do a substitution with, right? So if I try to substitute just p, then I'm not going to be doing anything. And if I try to substitute 400 minus p, then that's not really going to work, because then this is just going to become something like 400 plus p, right? So that means that doing a substitution straight away from this point is not really going to be that helpful. It doesn't seem like I can do an integration by parts. And so I need to come up with something else. Does anybody have an idea of how I could integrate that first, this left-hand side? Either in the chat or out loud in the mic. What techniques of integration do you know? I mean, if I'm giving you this problem, it's probably because you know how to integrate this. All right. Well, what we're going to be doing is we have a polynomial expression at the denominator, which is already factored. This is something times something at the denominator. And we have something of lower degree at the numerator. So that means I'm going to start doing a partial fractions technique over here to try to write this as something over p plus something over 400 minus p. Right? And the whole idea of trying to write this as something over p plus something else over 400 minus p is that first, I know that once I combine these two things, I'm going to get something that's on the denominator of p times 400 minus p. So that's the first really good thing over here. But the second thing is that I know that I can integrate each one of these pieces separately a lot more easily. This is very straightforward for the first term, and for the second one is either a little bit more thinking or a very easy substitution to do. All right, so I'm going to try to find the values of a and b. That will give me 1 over p times 400 minus p. And please raise your hand if you understand this. All right, so what I have is a over p plus b over 400 minus p, which means that when I put everything on the same denominator, I'm going to have a times 400 minus p plus b times p divided by p times 400 minus p. And what I want to make sure of is that regardless of the value of p, so for every single value of p that I plug into the left-hand side and into the right-hand side, these two expressions are the same, right? So I need this to be true for any given value of p, but because it has to be true for any value of p, it has to be true for particularly two values of p, which we're going to use in this case in order to find what a and b are going to be. So first, if p is equal to 0, and I'm going to choose p is equal to 0 because that way I know that I'll be able to get rid of the second term over here, and I'll only have to worry about the value of a. So I have that if p is equal to 0, then a times 400, so 400 times a, will have to be equal to 1 for these two sides to be the same, right? And I know that I only have to compare the numerators because the denominators are already the same, so I don't have to worry about that. Which means that a will have to be equal to 1 over 400. And then I'll have to evaluate this when p is equal to 400. And the reason that I want to do this when p is equal to 400 is because then I will cancel out the first term of the fraction over here, which means that I'll be able to only worry about the second term over here. So if that's the case, then I know that 400 times b will be equal to 1. Will have to be equal to 1. And so to guarantee this, I'm going to have to choose that b is equal to 1 over 400. Raise your hand if you understand this. I have Josh and Charles with their hands up. Were those questions or just? All right, okay. All right, so I have now the partial fractions that give me the left-hand side for this equation of integrals. So I'm going to be able to evaluate the integral on the left, and the integral on the right was easy to integrate regardless. And so this whole partial fractions thing was only a way for me to solve the first integral that I had over here. The right-hand side was really easy to evaluate to begin with. So that wasn't the part that I was writing about. So here I'm going to maybe separate the board first. And I'll have that. On the left-hand side, I'm evaluating the integral of 1 over 400 times 1 over p. So maybe I'll just write out the fraction right away. A over p, which is equal to 1 over 400 over p, plus b over 400 minus p, which is also 1 over 400, because I found that b was equal to 1 over 400 as well, over 400 minus p with respect to p. And on the right-hand side, I'm integrating k with respect to. So on the left-hand side, instead of having to drag the 1 over 400 for each one of the terms that I'm integrating, I'm just going to factor 1 over 400 out of my integral, and then I won't have to worry about that for a while. Right? So then I'll have 1 over 400 out of the integral over here. And I'll just have to integrate 1 over p plus 1 over 400 minus p with respect to p. And on the right-hand side, and here I'm going to start integrating right away. So I know that the antiderivative of k with respect to t is just k times t. And because I know that I'm only going to add the constant of integration on the right-hand side, then I'm going to do that right away. All right. And at this point, I still have 1 over 400, and now I'm actually going to evaluate the integral on the left-hand side. So first, the integral of 1 over p is ln of p. And the integral of the second term is ln of 400 minus p. But there's a catch. The 400 minus p over here was an inside function, a linear inside function, which means that once I integrated, I need to divide by the constant that would have come out when this was differentiated, right? So here, the constant that's multiplying the p is -1, and so that means that when I integrate, I'm going to have to divide by -1. And the important part that we said for this type of problem is we only are able to do this if the inside function here is a linear function, right? So here we have 400 minus p. That means the constant that's multiplying p is -1, so that's why I can't divide by that constant. Please raise your hand if you understand this. Okay. All right, so again, I'm going to try to avoid carrying the 400 on the left-hand side here. So what I'm going to start by doing in the next step is to multiply both sides by 400, which means that I get 400 times k times t plus 400 times c. And on the left-hand side, I end up with ln of p plus n divided by -1 is the same as minus ln of 400 minus p. Can I see a show of hands for those of you who have understood everything that we've done so far? All right, I have Jacob, John, Jennifer, Josh, Kastner, Lucas, Mackenzie, Mark, Parsa, Penelope, and Will that did not raise their hands. I'm wondering if there's maybe something that is not clear. Okay, so a couple other hands came up. All right, so what I'm trying to do in this problem, again, so like if we go back and we keep track of what we're trying to do, we're trying to solve the differential equation over here, which means that our goal is to find what P is, right? So an expression for the population as a function of time. Now, right now, I have ln of P minus ln of 400 minus P is equal to this whole expression over here, which is not ideal because we have already, like a bunch of terms. And what we want at the end is some kind of expression P is equal to something, right? So here we're going to have to put some effort into solving this equation in terms of P. At this point, we've finished solving the differential equation. What we're trying to do is to find the explicit expression of P in terms of P. So the first thing I'm going to do is, it looks like I have a logarithm on both of these sides. And if I could get rid of the logarithm, hopefully it would be easier for me to find the value of P. So I'm going to try to get rid of the logarithm. But to do that, I first have to write both of these logarithms as a single logarithm. So I'm going to start by writing this as ln of P. And if there's a minus, that means that this term over here has to be in the denominator of the inside function of my logarithm. And on the right-hand side, I'm going to keep writing this as 400k times t because I haven't done anything to the right-hand side. Okay, so I have now written this as a single function inside a logarithm, and the whole point of this is to try to use the same type of thing that we've been using since the beginning of this section, which is the fact that if I put a logarithm on the exponent of the number e, I get rid of the logarithm, right? So they're inverse functions, which means that if I do the exponential of a logarithm, of a natural logarithm, then the exponential and the logarithm cancel out, and I end up with only the inside function of the logarithm. That means here I'm going to have e to the power of ln of P over 400 minus P is going to be equal to e to the power of 400 times k times t plus 400 times c. Now, e to the ln of this is going to become just P over 400 minus P. And on the right-hand side, I'm going to break this sum in the exponent of e as a product, right? So that means I'm going to have e to the 400 c times e to the 400 times k times t. Now, again, instead of dragging e to the 400c all along and e to the 400kt, I'm going to try to give these a new name. So I'll have that e to the 400c over here. I'm going to write it as, what letter did I choose over here? A, just some number A. And e to the 400kt, I'm going to write 400k over here as some other value, which I'm going to denote by h. Okay, and this is because c is an arbitrary constant that I'm going to have to find. K is an arbitrary constant that I'm going to have to find as well. And so if I'm going to have to find c anyway, there's no problem in my writing this as, in writing e to the 400c as just another constant a, and instead of finding c, finding the value of a, right? And if it makes it simpler for me to read, then it's going to be easier to handle as I go. So that means at this point I have that p over 400 minus p is equal to a times e to the h times t. Okay, let's keep our goals in mind. What we're trying to do is find the value of p. Right, still my same goal from the beginning. But I have p at the numerator and at the denominator on the same term. That's a problem because I know that I can't break the denominator over here. It will be very, very bad to say that this is the same as p over 400 minus p over p, because I know that I can't break a denominator with a minus in that way. Right? If not, then all of the math would have been easier. Right? So instead, what I'm going to say is, well, if I can't break this in the denominator, what I can do is to try to multiply it over on the other side, because I know that if I multiply it, then I will be able to distribute this. So that's what I'm going to do. On the left-hand side, I'm still going to have p, but on the right-hand side, I'm going to write this as a times e to the ht. And I know that I'll be able to multiply this by 400 minus p. But even more importantly, I know that now because this is a product, I'm able to distribute the a times e to the ht. So I'll be able to multiply that over, and then it will be easy to separate both of these pieces. Right? So then I'll have that p is equal to a times e to the ht. So a times e to the ht times 400 minus a times e to the ht times p. Goals in mind still, what I'm trying to do here is to find p, right? So if I can, what I'm going to try to do is to put everything in terms of p on the same side and everything that's not in terms of p on the other side, which means on the left-hand side, I'm going to end up with p plus a times e to the ht times p, which is going to be equal to 400 a e to the ht. At this point, I can factor p from the first side. So this is 1 plus a e to the ht. And this is equal to 400 times a e to the ht. And finally, that gives me that p over here is equal to 400 times a e to the ht divided by 1 plus a e to the ht. Please raise your hand if you understand everything that I did so far. All right, at the next step, there's just one last piece of simplification that I'm going to do before I try to find the values of the constants. And that piece of simplification just relies on the fact that I have a times e to the ht at the numerator and a times e to the ht at the denominator. So what I could try to do is to divide both the numerator and the denominator by the same thing. I know that that's just like multiplying by a smart 1. I'm going to divide both sides, top and bottom, by a times e to the h. A e to the ht, and you're going to see why in a second. So at the numerator, I'm going to end up with just 400. At the denominator, I'm going to have this second term over here becomes just 1. So that means I have plus 1 over here. And then the first term is 1 over a times e to the ht. Now you might be saying, okay, well, miss, this doesn't look simpler. This is just 400, but then you have another fraction within the fraction. But lucky for me, this is an exponential, right? And because it's an exponential, I know that I can write e to the ht as e to the minus ht. So this will actually just be 400. And this is plus 1. And I can write 1 over a over here as some other constant, which I have called b for the sake of it. So this is b times e to the minus h times t. Why minus? Well, because this is at the denominator of the small fraction, which means that it has to have a negative exponent. Hands up if you understand this. All right. This is seriously the hardest type of problem that you're going to be able to solve, but you do have one problem like this in the web work. So it's not going to be enough to just understand what I did on the board. You're going to have to reproduce it yourself. Right now, we only have to find the values of b and h. So that's the last thing that we have for this problem, and we'll have just enough time to do that. So the first thing is that p of 0 is equal to 10. Which means that if I plug 0 into this expression, I should get the number 10, right? So that means that 400 divided by b times e to the 0, which is just 1, plus 1, is equal to 10. Now, if I have that 400 divided by something is equal to 10, that means that that something, b plus 1, should be equal to 40, because I know that if I divide 400 by 40, I will get 10. If not, of course, all that you would have to do is multiply both sides by b plus 1, divide both sides by 10. In this case, it's a little bit easier than that, which means that b is equal to 39. All right, so this has now gotten me the value of b, which means that I know that p of t, or p, is equal to 400 over 39 e to the minus h times t plus 1. And now I have to find the value of h, which is the only constant, the only piece that I don't have for my function. So I'm going to have to use the second piece of information that I was given, which is that p of 10 is equal to 45. So p of 10 is equal to 45, means that when I plug in 45 into this expression, when I plug in 10 into this expression, I should get 45. So that means 400 divided by 39 times e to the minus 10 times h plus 1 is equal to 45. From here, I multiply both sides by 39 e to the minus 10 h plus 1, and I divide both sides by 45, which tells me that 400 over 45 is equal to 39 e to the minus 10h plus 1. And if I simplify this a bit, I'm going to have that 39 e to the minus 10h plus 1 is going to be equal to 400 over 45 is the same as 80 over 9, if I divide both top and bottom by 5. This means 39 e to the minus 10h is going to be equal to 80 minus 9 over 9, so that's 71 over 9, which means that e to the minus 10h, if I divide both sides by 39, is going to give me that e to the minus 10h is equal to 71 divided by 351. Now, you don't get away from solving equations using exponentials. Here you have to find the exponent of e, so that means you're taking the natural logarithm on both sides, which gives us minus 10h is equal to ln of 71 over 351, which finally means that h is equal to ln of 71 over 351, the whole thing divided by negative 10. All right, so now by plugging into the expression that we have for p, we have that p is equal to 400 divided by 1 plus 39 times e to the minus 10 times h, so that's e to the minus h times t, minus h, which is minus ln of 71 over 351 divided by minus 10 times t. If I simplify this, I'm going to have that p is equal to 400 divided by 1 plus 39 times. The minus and the minus here cancel out, and I'm going to write this as e to the ln of 71 over 351 times t over 10, or the whole thing to the power of t over 10, right? So the same exact logic that we used before gives us that times t over 10, because it's at the exponent, it's like applying a second exponent of t over 10, which as a final answer gives me that 400, p is equal to 400 plus, divided by 1 plus 39, and e to the ln of 71 over 351 cancels out, which means that this is 71 over 351 to the power of t over 10. Please raise your hand if you understand everything that we did in class today. Okay, then really the only piece that's missing in order to solve this problem is to actually plug in 20 into this equation. So evaluate p of 20, which once you do this in your calculator by plugging into the exponent of this term over here, should give you a value of approximately 154. Yeah, approximately 150. So after 20 days, there should be approximately 154 fruit flies present. You can finish writing